When an engine fails on a multi-engine aircraft, there will be a decrease in thrust, and on propeller-driven aircraft, an increase in drag on the side with the failed engine. The results will be that the airspeed will decay, the nose will drop, but most significantly, the aircraft will yaw immediately towards the failed or dead engine. Controlling that yaw is of vital importance. The yawing moment is the product of thrust from the operating engine multiplied by the distance between the thrust line and the centre of gravity, the thrust arm, plus any drag from the failed engine multiplied by the distance between the engine centre line and the CG. The strength of the yawing moment will depend on three factors: how much thrust the engine is developing, depending on throttle setting and density altitude, the distance between the thrust line and the CG, the thrust arm, and the drag from the failed engine. If rudder is applied to counter the yaw, it will generate a moment which is the product of the rudder force multiplied by the distance between the rudder centre of pressure and the CG. At this initial stage, the pilot's ability to counteract the asymmetric yawing moment will depend on the rudder displacement, which affects the rudder force, the IAS, also affecting the rudder force, and the CG position, affecting the rudder arm. Under a certain combination of conditions, control difficulties can arise under asymmetric thrust. Let us assume that the live engine is at a high thrust setting, the rudder is at its full deflection, and the CG is at its rearmost limit, that is, giving the shortest rudder arm. If the IAS, the dynamic pressure, is just sufficient to produce enough rudder moment to counter the yawing moment, there will be no yaw. However, any decrease in the IAS will reduce the rudder force, and the aircraft will yaw uncontrollably towards the dead engine. This uncontrollable yaw, in this case to the left, will cause the aircraft to roll uncontrollably, also to the left, owing to the greater lift on the starboard wing whilst yawing left. The aircraft will enter a spiral dive to the left, which at the low speed would be impossible to stop with flight controls alone. If this were to happen close to the ground, the result would be disastrous. In these extreme circumstances, the only way to regain control would be to minimize thrust on the live engine or engines, to remove the yawing moment and permit a controlled forced landing. Thus, there is a minimum IAS at which directional control can be maintained under a given set of conditions after engine failure in a multi-engine aircraft. This minimum speed, which will vary with temperature and density, is called VMC, minimum control speed. There are different speeds for ground and air engine failures, and for different configurations. These are described fully in due course. One of the factors influencing the yawing moment following engine failure in a multi-engine aircraft is the length of the thrust arm. That is, the distance from the CG to the thrust line of the operating engine. In the case of a prop-driven aircraft, the length of the thrust arm is determined by the asymmetric blade effect of the propeller. At positive angles of attack, the thrust line of a propeller rotating clockwise when viewed from the rear is displaced to the right. This is because the downgoing blade generates more thrust than the upgoing blade. This phenomenon is fully explained in the lesson on propellers. If both propellers rotate clockwise, the right or starboard engine's thrust arm will be longer than that of the port engine. So, if the left engine fails, the thrust of the right engine acts through a longer thrust arm and generates a bigger yawing moment, and a higher IAS would be necessary to maintain directional control than if the right engine failed. Thus, at a given IAS, the given situation would be more critical if the left engine failed. The critical engine, then, is the one that would give rise to the biggest yawing moment if it were to fail. To overcome the disadvantage of having a critical engine on smaller twins, their propellers may be geared to rotate in opposite directions, or counter-rotate, with the downgoing blades inboard, giving both engines the shortest possible thrust arm. Bigger turboprop aircraft, such as the King Air and larger, will have co-rotating propellers, turning in the same direction. In the case of four-engine jets, either outboard will be a critical engine. Although the moments are balanced in the diagram on screen, the forces are not. The unbalanced side force from the rudder can be balanced in two ways, either with the wings level or by banking towards the live engine, which in a marginal situation is the preferred method, as will be explained shortly. In the wings level method, rudder is used to prevent yaw, and the ailerons are used to keep the wings level. Yawing towards the live engine gives a side-slip force on the keel surfaces behind the CG opposite to the rudder. The turn indicator will be neutral, and the ball central. This paradox of asymmetric thrust, where the aircraft is side-slipping but the ball is in the middle, is the exception to the rule of balanced coordinated flight. The advantage of the wings level method of balancing the forces is the strong horizontal visual and instrument reference available to the pilot. The disadvantages are that extra parasite drag from the side slip will reduce climb performance, which would be vital when close to the ground, and that there is a possibility of fin stall if the side slip angle is excessive, which would worsen directional control problems considerably. It is more aerodynamically efficient to balance the rudder side force by banking towards the live engine, so that lift gives a lateral component to oppose the rudder force. The bank angle must be restricted to 5 degrees to prevent significant reduction of the vertical lift component. Banking towards the live engine also reduces the side force on the fin from side slip, which effectively reduces the yawing moment and gives more rudder authority to stop the yaw. The cockpit indications on the turn coordinator will be no turn, but the ball will be out to the right. This is the corollary of the indication in the wings level method, there being no side slip, but the ball is not central. The advantage of this method is its better aerodynamic efficiency, without the side-slip drag penalty, making it better for use in marginal situations. But it is more difficult than the wings level method for the pilot to fly consistently. In practice, however, pilots will tend to use the wings level method initially, with its simpler handling references, usually combining the techniques only under marginal conditions, when the better aerodynamic efficiency of bank to the live engine or engines is of greater importance. The rolling and yawing moments, and the power of the flight controls to balance them, will determine the controllability of an aircraft with asymmetric thrust. These rolling and yawing moments are affected by thrust on the live engine. Yawing moment increases with thrust, and the further out the engine is mounted on the wing, the larger the moment. Thrust is greatest at low speed and maximum power. Thrust reduces with increases in altitude and temperature, that is, higher density altitudes. The worst case for an engine failure is thus after takeoff at sea level on a cold day. The drag from the propeller itself will depend on whether it is stationary, windmilling, or feathered, but there will always be some contribution to the yawing moment. If the propeller is stationary, it is generating some drag from the blades, which could be at a relatively large angle to the airflow, but no torque. A windmilling propeller will produce a large amount of drag, being driven by the relative airflow, generating both drag and torque. The propeller will also have the load of turning the dead engine, unless an automatic decoupling device is fitted. A feathered propeller will cause the least possible drag. There is no torque, since it is not rotating, and the parasite drag is at a minimum with the blade's edge onto the airflow. If both engines rotate clockwise, the right engine has a longer thrust arm, and failure of the left engine gives a greater yaw moment. This asymmetric blade effect, or P factor, is absent with counter-rotating and contra-rotating propellers, and of course on jets. The aircraft rotates around its CG, but its fore and aft position has no effect on the yawing moment from a failed engine. The rudder arm is affected, however, with an aft CG giving the worst case with the least rudder effectiveness. When the engine turns the propeller, the equal and opposite reaction tries to turn the engine the other way, the torque effect being to roll the aircraft to the left. If the left engine were to fail, it would result in a bigger rolling moment to the left. As with asymmetric blade effect, this happens only with co-rotating propellers. Note, however, that if the propeller is windmilling, the torque is reversed, but is much less than the torque of the live engine. Any propeller-driven multi-engine aircraft will suffer a loss of lift from the slipstream-induced faster airflow over the wing behind the failed engine. The reduction in total lift will give a tendency to descend, but more importantly, a roll towards the failed engine. The roll is exacerbated if flaps located behind the failed engine and its counterpart on the live side are down, owing to the higher CL. If the aircraft is being flown wings level asymmetric, it will be side-slipping, and the dihedral of the forward wing, in this case the port or left wing, will generate more lift, compensating in part for the loss of lift from the slipstream. Any weight increase will require a higher angle of attack at any given speed. This will have the result of increasing asymmetric blade effect with a bigger yawing moment, and partially masking the fin and rudder, making them less effective. Ultimately, the most important element in the control of the aircraft under asymmetric conditions is dynamic pressure, which is a measure of the calibrated airspeed, CAS, which is, in turn, indicated airspeed, IAS, corrected for position error. IAS, of course, is what the pilot sees on his airspeed indicator. Higher IAS means more control effectiveness, and consequently greater rudder movement, all other parameters being unchanged. We can summarize the factors affecting the roll and yaw moments when on asymmetric thrust as follows: thrust on the live engine, altitude, drag from the dead engine and propeller, asymmetric blade effect, center of gravity position, torque reaction, difference in lift from slipstream, rolling moment due to side slip, weight, and finally the vital element of IAS, which determines the amount of control the pilot has over the aircraft.